Today we're going to look at calculating the expected value of a discrete probability distribution. And we're going to use this to analyse the variance and standard deviation, ultimately looking to find a 95% confidence interval. Now the expected value of a function is really what we'd call the mean. It's what we expect to happen given enough trials. It looks quite complicated, and when we have a look at the formula here, we'd say that E of x is the sum of, that's what that capital sigma means, x times p of x. Now like I said, it looks like it's quite complicated here with this capital sigma, but really all we need to do is say, let's look at what x is and multiply it by its corresponding probability. So in an example below, if we wanted to find E of x, we would say that 0 times a plus 1 times b plus 2 times c plus 3 times d. And so you can see as I've structured it below, that's a 3d, 2c, 1b, and we wouldn't expect a. Now we can apply this to a practical situation. It says here that a person may buy a lucky ticket for $1. They have a 20% chance of winning $2 and a 5% chance of winning $11. Otherwise they lose. The question asks, is this a good game to play? Now oftentimes this is a difficult question simply because people aren't sure what they're supposed to do. But if it's asking, is this a good game? Or if it's asking, should you evaluate, any question that might ask you to evaluate this, we need to have a look at the expected value. So if a person buys a lucky ticket for $1 and they lose, then we might think to ourselves, let's let x be the net profit or the net gain. So if we let x equal net gain, I set up my table here with x and p of x, the chance that it would happen. We know that we could lose $1. We know that we could gain $1, because if I spent $1 on the ticket and I won $2, I'd be gaining only $1. And if I spent $1 on the ticket and won $11, then my net gain here would be 10. Now I know that I've got a 20% chance of winning $2. So here I can put 0.2. I know that I have only a 5% chance of winning $11, so we can put 0.05. And the key phrase here, otherwise they lose, tells me that the remaining percentage here is 0.75. Now I got that by thinking 1 minus 0.2 minus 0.05, because I know the bottom row must equal to 1. Now remember the question here said, is this a good game to play? And we'll find that out by looking at E of x. So E of x is equal to the sum of x times p of x. So that is, it's equal to -1 times 0.75. And so I'm getting that by multiplying that column, plus 1 times 0.2, which we get by multiplying that column, and then plus 10 times 0.05. So we can add 10 times 0.05. Now ultimately we get negative 0.75 plus 0.2 plus 0.5, we end up with negative 0.05. So the question is, what does this actually mean? If we're expected, on average, to lose 5 cents, then this would not be a good game to play. So it's important that we can demonstrate to the examiner or the person marking this that we know what we're talking about. We can recontextualize our answer. So we would say something along the lines of, this is not a good game to play as on average we are expected to lose 5 cents each time we play. Let's just give ourselves a bit more room there. Each time we play. Looking at how we can extend this to an example, it says here that a coin is biased in favour of heads. So that's a good bit of context here, such that the probability of obtaining a head on a single toss is 0.6. So the thing that I would be measuring here, it says if, well, actually we'll get to that. Let's just jerry that the probability of obtaining a head on any single toss is 0.6. The coin is tossed 3 times. The result is noted. And I know that x is the number of heads obtained. The question has asked me to find e of x, the expected value of x. We also know that to be the mean. So let's start with what we know. We know that x equals the number of heads obtained. We know that the probability of getting one head is equal to 0.6, which leaves the only possible outcome, the probability of getting a tail, equal to 0.4. Now if the coin is tossed 3 times, I might list my sample space, which I could do either by drawing up the tree diagram or by thinking about the pattern we know. If this is tossed 3 times, then I'm going to have heads, 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 tails, 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 tails. There's my pattern of 4. Now we move to a pattern of 2. Heads, heads, tails, tails, heads, heads, tails, tails, and our pattern of 1. Heads, tails, heads, tails, heads, tails, heads, tails. I know that's a bit arduous, but this here is our sample space epsilon. So, before I can find an e of x, the reason why I'm listing this sample space is because I will need to have a probability distribution table. So I'm going to need to have something along the lines of x, a chance of getting a head, or rather the number of heads obtained, p of x, the chance of getting that. I know that in 3 tosses I could have 0, 1, 2, or 3 results of a head. Let's start with 0. It's something rather easy to obtain. When I have a look here, I think, which one of these presents the 0 case? The only time there is no head is right at the bottom here, where we would get a tail followed by tail followed by tail. So how do we do that? Well, that's 4 over 10 times 4 over 10 times 4 over 10, given that our chance for a tail was 0.4. So that's 4 cubed over 10 cubed, which is 64 on 1,000, or 0.064. Now the next case is looking at, well, in what situation would we get just one head? So if I'm looking here where x is exactly 1, I can see that I've got heads, tails, tails as an option, tails, heads, tails as an option, and I need to find something in which there's only just one more head, which is at the bottom here, tails, tails, heads. Now due to our associative law of mathematics, where we know a times b is the same as b times a, the single chance here will always be the same. A head would be equal to 0.6 and 2 tails would be equal to 0.4. So we've got 6 over 10 times 4 over 10 times 4 over 10. Tail heads tail would be 4 over 10 times 6 over 10 times 4 over 10, which we know will be the same value as before, and also 4 over 10 times 4 over 10 times 4 over 10. So instead of writing all of that out, because I know the associative law, all I'm going to say is we've got 3 times, in brackets, 1 head and 2 tails. So we've got 16, which is 4 times 4 over 100, and 16 times 6, which is 96 over 100, and 96 times 3, 90 times 3 is 270, 6 times 3 is 18, so we end up with 288 over 1000. So I know my chance would be 0.288. Now looking for the case in which there are 2 heads, over here, we need to see that we could have heads, heads, tails, heads, tails, heads, and tails, heads, heads. Now as with the previous result, I know that all 3 of these will be the same thing, whatever that might be. And to calculate it, we think there's 1 head, there's another head, and there's 1 tail. So 6 times 6 is 36, 36 times 4, 30 times 4 is 120, 6 times 4 is 24, so we've got 144 times 3. Well, 140 times 3 is a bit like saying 14 times 3. So 140 times 3 is actually 420, plus 4 times 3 is 12. It gives us 432 over 1000. So I know that's 0.432 over 1000. Now the last and at this point only possible one is to have 3 heads, which we can see here. Now 3 heads would be equal to 6 over 10 times 6 over 10 times 6 over 10, or 6 cubed over 1000. So 6 times 6 is 36, 36 times 6 is 216 on 1000. I could check my answers at this point by making sure that my numerator adds up to 1000. 64 plus 288 plus 432 plus 216. You can check it yourselves, but it does indeed add up to 1000. So I know my P of x adds up to 1. Now all of this work hasn't actually had me make any progress on finding E of x. It's just given me the tools with which I can do that. It's given me what I need, which is the probability distribution table. But to answer the question itself, we might think, remembering E of x is equal to the sum of x times P of x. So that's going to be equal to 0 times 64 on 1000, which we know is 0, plus 1 times 288 on 1000, which we know is 0.288, plus 2 times 432 on 1000, so that would be plus 864 on 1000, so 0.864. And finally, we would add 3 times 216. Well, 3 times 200 is 600. 3 times 16 is 48. So we would have 648 on 1000. Now I could use my calculator to add these up, or you guys could just trust me that the answer is 1.8. So we would expect to get 1.8 heads if we tossed the bias coin 3 times. Now sometimes it's not quite as simple as just saying the expected value of x. Occasionally we might want to apply a function to that x. Now this looks a little bit complicated again, up here saying that e of g of x is equal to the sum of g of x times p of x. Looks complicated, but really there's only one difference. Instead of x, we've got g of x, and that appears exactly the same way in the formula. So all that has to happen If, for example, my g of x, as it is in example 2, was 3x plus 1, is instead of taking that top row, I'll now take each number in that row, multiply it by 3, and add 1. So that g of x in this case is really just found in there. So the question here, for the random variable x to find in example 1, find e of 3x plus 1. Well, let's just go back and we'll get our table. We knew that we could have had our x and our p of x. We had 0 heads, 1, 2, or 3. And we knew that our chance was 0.064, or it was 0.288, 0.432, or 0.216. Now from here, if I wanted my 3x plus 1, I might make a new table with g of x. So I might just drop this down further. And I'll say, okay, now I've got 3x plus 1. So 3 times 0, 3 times 0 plus 1 is 1. 3 times 1, which we're getting from up here, is 3, plus 1 is 4. 3 times 2 is 6, plus 1 is 7, and we got it from here. 3 times 3 is 9, plus 1 is 10. So now, my e of 3x plus 1 is equal to 1 times 0.064 plus 4 times 0.288 plus 7 times 0.432 plus 10 times 0.216. And so whatever it might mean to apply this linear transformation to x, we know that once we do it, the expected value of such a thing works out to be 6.4. Now this was for part A in the question. For part B, we're asked to find e of x squared. So we can do this in exactly the same way. We thought that our probability distribution of x was 0, 1, 2, or 3. We knew that our chance, or our p of x, was 0.064, 0.288, 0.432, or 0.216. But now we need to think to ourselves, well, what's my x squared? So my x squared is going to be 0 squared, that's 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So we know that we're getting this value, this value by squaring that one. And this value by squaring that one, this value by squaring that one, this value by squaring that one. I think at this point you get it. So, e of x squared, and I'll just make sure I've got some room here, e of x squared is equal to, well, there's still 0 first, when we look at this, plus 0.288, that still hasn't changed, plus 4 times 0.432, which is here, plus 9 times 0.216, which we get from there. Now when I total all of this up, I find that e of x squared is equal to 3.96, and you could use your calculator to work that out. Now this example is really the same thing. However, constructing the probability distribution table is difficult for different reasons. You can see there's a large slab of text here, and finding out exactly what we need will take some time for us to read it and break it down. So let's start with what we have. It says for a $5 monthly fee, so there's a thing, a TV repair company guarantees customers a complete service. The company estimates that the probability that a customer will require one service, so the probability, here's a thing, the probability that a customer requires a service call is 0.05 in the month. The probability of 2 calls is 0.01. So right now I might think to myself, okay, and the probability of 3 calls we know doesn't really matter because 3 or more calls gives a probability of 0.0. Now some more context here is that each call costs the company $40. So for every call out there's a $40 cost. And the question asks, what is the TV repair company's expected monthly gain? So there's 2 things to consider here. Yes, we know the probability of a call out, but that's not really what we're after. What we're after is what is the expected gain or the expected net benefit after we've drawn a fee and after we've incurred our costs. So let's start with what we think we have here. We could call X the number of calls. So if I said X here, we could get 0, 1 or 2 calls. We're not going to worry about 3 or more as it's a 0% chance. We know now that if there was no call out, our gain, let's just call it G, would be $5 when there's no call out. If there's 1 call out, then we've earned our $5 fee, but we've incurred a cost of $40. So as a company, we've actually lost 35. We signify that with negative 35. Now 2 call outs, that would be $40 per call out, so it's a negative $80, but we've still made that one $5 monthly fee, so our gain here would be negative 75. Now we can start to input our probabilities. Now we don't really want to talk about the probability of X, we're really looking for the probability of G. The probability of a $5 gain, which is the same as the probability of not getting a call out, we don't know that yet. But we do know that the probability of 1 call out is 0.05 in the question there. It's 0.05. We know that there's a 0.01 chance, or a 1% chance, that you'll get 2 call outs. And we know that the remaining, which we see, I believe it says all the other things that we can assume there would be no call out, would be 1 minus 0.05 plus 0.01, so 1 minus 0.06 or 0.94. Now to find our expected gain here, we're going to sum G times the probability of G. So we're going to say 5 times 0.94 plus negative 35 times 0.05 plus negative 75 times 0.01. And that ends up being 2.2. So to put our answer in context, we might come up here and we'll say that each customer each month generates $2.2 gain. And that's our expected gain. So far we've looked at the expected value, which really we can think of as our measure of centre. It's a measure of the average. We're now going to have a look at 2 other measures. One is variance and one is standard deviation. Now both of these things are a measure of spread. So what we're saying here is rather than measuring what the average value is, a good way to think about this is if we randomly selected one person, how likely or how close will they be to that expected value? Now, the simplest example I can think of is this. Imagine we had 10 people, 5 of whom scored 100% on our test, and 5 of whom who scored 0%. The average mark would be 50%. So if 5 scored 100, 5 scored 0, and if I asked someone randomly what is their score, they would never ever get a score of 50. In fact, no matter who I asked, their score would always be 50% away from that 50. And so really, that measure of centre, that mean average of 50%, is quite useless to us. In fact, even the median in that case would end up taking the midway point between 0 and 100 and end up also being 50, which doesn't help us. This is the reason why we have to look at the measure of spread. It gives us a far bigger story. Now, the first formula for variance, the one that the study design would like us to know, I really don't care if you look at. I don't find it very useful, and I think it's difficult to understand. What I'd rather you look at is that the variance of x is equal to e of x squared, something we know how to calculate. So something we know that we just take that x value, we square it, and times by p of x, and we minus e of x all squared. So if we've calculated the expected value, we square that afterwards. Now, standard deviation is another measure of spread. It uses the lowercase sigma. That's kind of universal across the board. When you see sigma, you know that it's referring to standard deviation. Now, sigma is defined, or standard deviation is defined, as sigma squared equals var x. So the square of the standard deviation is what variance is. In other words, we can find the standard deviation sigma by square rooting the variance. So we'll find variance first and get the square root of that. You might be wondering, what does the standard deviation tell us? Well, if we had a large data set and we knew what the median was, we can assume, one, that it's normally distributed, and we'll get to that later. But generally speaking, if we took the average and we added 2 sigma, and we said, okay, that's an upper bound now, and we took the average again and we subtracted 2 sigma, what we'd know is that about 95% of the data lie between that. Now, if we took the median and plus or minus 2 sigma, we'd know that certainly 95% of the data falls between that. But because we don't have the median, and because instead we have the mean, or the expected value, we know that that's pretty close, and so we know that this is approximately 95%. So we can find a good approximation for the 95% confidence interval simply by taking our mean, our expected value, sometimes called mu, and adding or subtracting 2 sigma. So we can see what this looks like in practice with a fairly straightforward question. It says here that a discrete random variable x takes the values 0, 1, 2, 4, 8. And the probabilities are shown in the table here. There's no great context here. We don't have to interpret anything too deeply. We know that these are our values. And the first thing I'd hope you'd realise is that there's a big P there. Fortunately, the first question says, find P. We can use our identity that we know that all the probabilities must add up to 1. Therefore, 1/2 plus 1/4 plus 1/8 plus 1/16 plus P has to equal to 1. Now, 1/2 plus 1/4 plus 1/8 plus 1/16, if you get a common denominator of 16, we'll get 15 over 16 plus P equals 1, and so I know P equals 1/16. Let's just write 1/16. that was part A. Part B asks us to find E of x. Well, I know what E of x equals. That's going to be 0 times 1 on 16 plus 1 times a half, which is a half, plus 2 times a quarter is also a half, plus 4 times an eighth, a half again, and 8 times 1/16. So my E of x is equal to 2. Part C is asking us to find the variance. Now I know that the variance of x is E of x squared minus my E of x squared. Well, let's try E of x squared. If I added a new column to this table, x squared, I said, well, 0 squared is 0, 1 squared is 1, 2 squared is 4, 4 squared is 16, 16 squared is 64. Now, E of x squared is still going to be 0 times 1/16 plus 1 times a half. This time it's plus 4 times a quarter. It's plus 1. Plus 16 times an eighth is plus 2. And 64 times a 16th plus 4. And so I know that E of x squared is 4 plus 2 is 6 plus 1 is 7 and a half, 15 over 2. Now my variance, which is what we were asked to find, is equal to 15 over 2 minus, well, we need something squared here. That's my E of x over here, minus 2 squared. So 15 over 2 minus 4, or minus 8 over 2, is 7 over 2. If we wanted to add a part D, find the standard deviation sigma, well, that would be simple. My standard deviation would simply be the square root of 7 over 2. If I wanted to rationalise that, I don't need to, but I could call that, if I times by root 2 on root 2, root 14 on 2. And that's equal to sigma. Now looking at example 5, it says that a manufacturer knows the mean number of faulty light bulbs in a batch of 10,000 is 12. That's a long sentence to tell me that the mean is 12. This sounds so obvious when you think about it, but if you're wondering what are the important bits of information in the question, look for the word the. It's going to usually be followed by something pretty important, the mean. Then look for the next time you see the word is. The mean is 12. The standard deviation of 3. So they're two pretty big pieces of information. I might start with the fact that mu equals 12 and sigma equals 3. Now the manufacturer, he wishes to claim to his clients that 95% of batches, so he's looking for a 95% confidence interval, will contain between C1 and C2 faulty light bulbs. What are the two possible values of C1 and C2? So what I need to know here is that this manufacturer is looking to say, whoops, we'll just get a pen out, the probability of C1 less than or equal to X, which is less than or equal to C2. So what are the possible ranges within this batch of 10,000 for which 95% of the data, he could say with confidence, would not be faulty? So that wasn't a very well worded way to say that. Let's try that again. The two possible values of C1 and C2 are saying that we know 95% of batches will contain between C1 and C2 faulty light bulbs? Well, we know something for a really good approximation for about 95%. What we know is that the probability of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma, well, that's about 0.95. So if I calculate this being 12 minus 2 times 3, so 12 minus 6 is 6, and this being 12 plus 6 is 18, then I could say the probability of 6, or x being between 6 and 18, is about 0.95. Now I've almost answered the question. Remember that the question's asking me the possible values of C1 and C2. And so in this case I would say C1 is equal to 6 and C2 is equal to 18. Finally today, we're looking at example 6. It says the number of chocolate bars X sold by a manufacturer in any month has the following distribution. So the most important part there is I've got a distribution table. What is the probability that X takes a value mu minus 2 sigma to mu plus 2 sigma? Now this is a question that personally I find so frustrating, because most people, and the way it's worded I think sets you up for this, you're thinking, well, what is the probability that X takes this thing that looks like our 95% confidence interval? Naturally we just want to say that it's 0.95. And yet that's not quite true, because this is discrete data and we knew that it was an approximate. So we're going to need to work this interval out, apply it to the table, and then see how much of the data we can cover. So let's start with finding mu. We know that mu is basically the same as E of x. So we've got 100 times 0.05 plus 150 times 0.15 plus blah blah blah. I'm thinking you get it at this point, that then we get to 400 times 0.05. So our expected value for x we find as 225. So a good way to think about this is on any given month we can expect, or the manufacturer can expect, to sell 225 chocolate bars. Now we also need to find sigma so that we could find mu plus or minus 2 sigma. Well, let's start with finding the variance. The variance of x is equal to E of x squared minus our E of x, our 225 squared. Well, we know E of x squared just means that we square all these numbers at the top and multiply them by the probability. So 100 squared times 0.05, 150 squared times 0.15. And so you can use a calculator for this, and our E of x squared is 55,000. So we've got 55,000 minus 225 squared, and again our calculator will yield a result of 4,375. But remember, we're not after variance, we're after standard deviation. So if we come all the way back up here, we would say the square root of 4,375, we only need to go to 2 decimal places here, is 66.14. Now we're almost there. Our mu minus 2 sigma, well, our mu is 225. So on one barrier here we need to say 225 minus 2 times 66.14. And so our lower bound is 92.72. Our upper bound, mu plus 2 sigma, is 225 plus 2 times 66.14. And our upper bound here is 357.28. Now here, we need to look at the fact that this is discrete, that it's not continuous, and we can't just have these decimal answers. So looking at my probability distribution table, I know I've got options for 100, 150, 200, 250, etc. The reason why this might be the case is we may well only sell boxes of 50, for instance, and you can either buy 50 or you can buy none. So we need this to be discrete. The best way to model how we round this, I feel, is to start with a number line. So let's just bring up a ruler here, and we'll start with a number line. Suppose I've got 50, 100, 150, 200, 250, and we can go all the way up to 300, 350 and 400. When I look at my distribution table, I see that there's 100, 150, 200, 250, 300, then 400. So this 350 isn't really an option. And so I might just put in 400 at the end there. I also know that this 50 isn't really an option, and so we can assume, in that case, a 0. Now my bounds, found before, the first one was 92.72, so we know that it's this side of 100. And the second one was about 360, so I know that it's closer to 400. And if I rule that up, we can join the dots like so. We've got a good estimation, or a good visual estimation of where we're at. Now the question is, how do I relate this back to my question? Well, we always round towards the centre. So if I imagine that I had something in the centre here, we always need to round towards that. So although I've gone, I suppose one way to think of it is over 100, I need to backpedal and stop at 100. And although I'm closer to 400 than I am to 300, I haven't crossed 400, and I need to round toward the centre, so I'll round to the 300 mark. And so this idea of mu minus 2 sigma being 92.72, we now need to change so that it matches our discrete table, and say that the probability of 100, where we rounded to, less than or equal to x, less than or equal to 300. This now represents our mu minus 2 sigma and our mu plus 2 sigma. And if I have a look at my table, I've got 0.05, 0.15, 35, 25, 15. The only thing I don't have is that 0.05. And so 1 minus the sum of all those purple values is actually 0.05. So in fact, if I add them all up, I get 0.95. Now I want to stress that the answer here was not 0.95 because we were asked to find something that looked like our confidence interval. We needed to do this really important step of rounding towards the centre and then relating back to the question at hand. Now in summary, we know that we've been able to find our E of x as just being the sum of x times P of x. We know that our variance was equal to E of x squared minus the square of E of x. And we know that our standard deviation is the square root of this calculated variance.